All right, today we're going to continue with our discussion of entropy and enthalpy, but we're going to relate it to free energy. So we've been dancing around delta H and delta S, and now we're going to talk about delta G and how that fits in. We're going to explain the relationship between the sign of the free energy change and whether or not a process is spontaneous in the forward direction. There's going to be a lot more calculations in this one, so I'll try to keep it quick. It's pretty much the same equation we've been using, just a variation of the same thing, right? The delta, the change of whatever your products are minus the change in your reactants gives us your overall change, right? So our first one, here's a standard free energy change. It says find the free energy change, or sorry, free energy of formation for the oxidation of water to produce hydrogen peroxide, given the following information. Well, all we need to do is add up the sum of our products and the sum of our reactants, and of course we need to keep it proportional to our moles, and we should be able to find our delta G. So the only product we have here is our H2O2. All right, and then we're going to subtract 2 times my H2O values. I'm going to put parentheses around that, plus my O2. Okay. The nice thing is this is where standard states come in again. Delta G and delta H typically have standard states where things are 0. So O2 is in the standard state. This time they tell us it's 0, so we can actually cross that part off in our equation, and we end up simplifying. We get 2 times 2 H2O, sorry, H2O2, hydrogen peroxide, minus 2 times H2O. All right, and let's plug in. We get 2 times negative 27.2 kilocalories per mole. All right, and we're going to subtract that 2 times negative 56.7 kcals per mole. Okay, so we're going to have to be careful with our signs there. 27.2 and 56.7. All right, 2 times negative, what did we say, 27.2, close parentheses, minus 2 times negative 56.7, okay? Make sure you put parentheses around it, because what ends up happening in, our second half, our reactants half here, is we are subtracting a negative, which means we're really adding. So we end up getting a positive 59 kcals here. Ooh, there you go. So we end up getting a positive 59 kcals per mole here. All right, and that would be our delta G. Let's evaluate, is this spontaneous or non-spontaneous? It's a positive value, therefore it is not spontaneous. All right, non-spontaneous. All right. Okay, here's another one. This time we have to look at our table and look up our values, but be careful because the states of matter do in fact matter. When we look these things up, we look at the table right now. Potassium chlorate has both an aqueous state, that is here, and a solid state. If we're looking at this table, delta GF is in this middle column here. So we've got negative 408.3. So negative 408.3 kilojoules per mole for KCl. KClO3 in the solid state is negative 289.9. So negative 289.9 kilojoules per mole. And then oxygen, believe it or not, because it's in the standard state. What was it? Saw it earlier. Here it is, O2. The standard state of gas is 0, an entropy of 0, or delta G of 0, sorry. So I've got kilojoules per mole. Okay, so in our setup, we got products minus reactants. Alright, the nice thing is this is a 0. We can take that out. Got negative 289.9 kilojoules per mole. We subtract that from negative 408.3 kilojoules per mole. There you go. Careful of that negative sign when you do your math, because if we minus a negative, it's really like adding a positive. So negative 289.9 minus negative 408.3, and we get a positive 118.4. All right, 118.4. .4 kilojoules per mole. That is our delta G. Let's check ourselves. There we go, we're on track, good. And let's evaluate, is this going to be spontaneous or non-spontaneous, and why? Okay, it is non-spontaneous. It is a positive delta G. You can also look at it in terms of entropy. We are creating order, therefore it's not likely to be spontaneous. Alright, here's another one. We still have to look up our values here. So we can use the same value as before for KClO3. KClO3, we said negative 289.9, negative 289.9 kilojoules per mole. Alright, KCl solid, that was the negative 408.3. And this time we got a new thing in here, O3. So O3, if we look at our table, O3 is 163.4. That's in this section here. 163.4. 163.4 kilojoules per mole. So let's get our setup here. We've got our products. So 2 times O3 plus 2 times KCl, close brackets, minus 2 times KClO3. All right, so our brackets there. I trust you can plug in. Go ahead and try the math for yourself on this one. Let's see what we get. All right, here are my numbers. I've got 2 times 163.4 plus 2 times a negative 408.3 minus 2 times negative 289.9. Okay, so here are our numbers plugged in. 2 times 163.4 plus 2 times negative 408.3, and then we add those together, subtract a negative 289.9 times 2. So let's rock that in our calculator. We got 2 times 163.4 plus 2 times negative 408.3. Negative 489 plus, well, so we subtracted, sorry, I should say minus 2 times negative 289.9. All right, and we get a positive 90. And that is what we got. Let's confirm. Positive 90 kilojoules. Okay. Our answer matches up. We should be good to go. All right. So it's time to look at the free energy changes. We have this equation, you've seen this before in honors, delta G equals delta H minus T times delta S. Now we have to be careful again because delta G is in kilojoules per mole, delta H is in kilojoules per mole, but delta S is in joules per mole K. So that's going to make some issues when it comes to doing the math. All right. Now the nice thing is that delta G and delta H always mean the same thing. When we're talking about a positive delta G, it is non-spontaneous. And negative delta G is spontaneous. All right. And spontaneous is usually paired with an exothermic reaction, meaning heat is released. Non-spontaneous, heat's being absorbed. Endothermic, sorry. Delta S is where it's switched. Positive means more disorder, and negative means order. So this last problem, yes, this is my last problem. This one's a doozy, mainly because it asks you to do all three parts. So it says that we have this synthesis reaction carried out at 25 degrees and 1 atmosphere. Calculate delta H, delta S, and delta G using the following data. So I give you delta H values and delta S values. And we also know we have this equation in the end, delta G equals delta H minus T delta S. Lovely. We got to use all three. So we've got our delta H. Delta H is going to be equal to the sum of the delta H products minus the sum of the delta H reactants. And I'm going to go ahead and plug in my numbers there. Nice thing is I've got 0 for my oxygen, so my products are just 2 times my SO3 minus 2 times my SO2 values. All right. So 2 times negative 396. And that's going to be the subtraction of 2 times negative 297. All right. So 2 times negative 396, and we're going to subtract 2 times negative 297. Right. Get a negative 198 kilojoules per mole for delta H. Take a moment and evaluate. Is this endo or exo? It's exo. It's a negative delta H. All right, we're going to do the same thing with delta S, except I'm going to skip some steps. We know same process, products minus reactants. This time I have to include my oxygen because I have a value. So I've got 2 times my products, 2 times 205 joules per Kelvin mole. All right, and I'm going to subtract 2 times 248. Oh, I'm sorry, I plugged the wrong number in here. This is supposed to be for SO3. SO3 is my product, so 257 here. I've got 248 for SO2 plus 1 times my oxygen value, which is 205 joules per mole K. All right, so we've got SO3, SO2, and my oxygen. Okay, so we've got 2 times 257 minus, we had 2 times 248 plus 205. We had a negative entropy here too. All right, so negative 187 is our delta S. Okay, and that's joules per mole and Kelvin. All right, evaluate that real quick. Does that number tell us that we are creating order or disorder? We are creating order. You can also check that by looking here. It's a synthesis reaction that is also creating order. All right, so we've got so far delta H is equal to negative 198 kilojoules per mole. Delta S, delta S is equal to negative 187 joules per mole K. And we're told that we're at 25 degrees Celsius, which means we're really at 298 K. So let's use my equation, but before I use my equation, I need to convert this to joules because otherwise this is not going to work out very well for me. All right. So delta H is really going to be this many joules per mole. So delta G equal to 198,000, sorry, negative 198,000 because of my sign. Joules per mole. So negative, right? That's what I was given here. All right. Minus 298K times negative 187 joules per mole K. All right. Let's put those in the calculator together. Negative 198,000 joules minus 298 times negative 187. All right. We get negative 142,274. So we get negative 142,274 joules. Everything we see so far is in 3 sig figs, so let's get this to 3 sig figs and let's convert it to kilojoules. This is going to be a negative 142 kilojoules per mole, and that is my delta G value. All right, so this is interesting. This goes along with what we said in the last play posit. Even though we're creating order, we're releasing so much energy that this is still what kind of reaction? It is spontaneous. Yes, negative 142 means it is spontaneous. So the amount of energy being given off just gives off so much energy in this reaction that doesn't matter that we're making it more ordered. It just matters that we're more favorable by giving off this much energy. Okay. That is all for today. Have a great night.